We have seen how the trend line could be used to get predicted values and incremental values. We have said then that the trend line is the line that fits linear relationships best. But what does that mean exactly that it has the best fit? This is what we are going to talk about in this video. First, I want to introduce a concept called the residual. The residual is the difference between the value that you observe and the value that you predicted. So a residual is how wrong you were when you made the prediction. If we look at the plot on the right, we have two variables, y and x, and we have a sample of points. If I add a trend line to that, we could begin to compare what we observe to what we would have predicted based on this trend line. In this case, let's say at x equals 0, we observe a blue point and y is roughly equal to 2. That's if we look at the point. If instead we look at the trend line to make a prediction, the predicted value y hat would be 0. So the residual is the difference between y and y hat. It is how wrong we were when we guessed 0, when in fact we observed that the real value was 2. Now, the residuals can be either positive or negative. If you underpredict, the line is below the point that you predicted, then your residual will be positive. If you overpredict, your residual will be negative. So now we are prepared to understand the trend line and why it is the line of best fit. Another name for this line is the least squares line. The reason why we call it the line of best fit or the least squares line is because here we are defining the best to be the minimum of the sum of the squared residuals. If we look at the plot on the right, each residual is represented by a red line. So if we square them, the result will be equal to the area of each corresponding red square, since the area of a square is the square of its side. Now, why do we square them? One reason is that we are going to sum these squared residuals, and if we didn't square them first, then positive and negative values would cancel out. For instance, if we had a predicted value that is very wrong and we had a residual of plus 10, it could cancel out with another predicted value that is also very wrong, but with a residual of minus 10. When we square them, however, we get 100 plus 100 for both minus 10 and plus 10, so they don't cancel out when we add them. Now you might ask, why not use absolute value instead of square? First, we want to penalize big residuals more. If the residual is 1 and we square it, we still have 1. However, if the residual is 10, it becomes 100 when we square it, which is a lot larger. A second reason is that if we use absolute values, there could be many different trend lines that would be a good fit, and we wouldn't know which one to pick. Finally, there are other important properties, but if you want to know them, you will have to take a course either in econometrics or in regression statistics. Now, let's visualize the sum of the squared residuals. On the left, we have the squared residuals, and you can see that I'm starting to add some equations under the plot titles. So the equation is y minus y hat squared. On the left, we sum these squared residuals, and if we get the total area, it's represented by the red box. It looks like this. In the equation, the symbol that looks like a large capital E on the right, it's a capital sigma, and it represents the sum in mathematical notation. Now, what happens if we change that line of best fit? What happens if we change the slope? Let's make it a little bit steeper. We can see that when I do that, some of the points now are closer to the line. So our residuals will be smaller for these points. But for some other points, they are going to be greater because the points are further away from the line. We can calculate the squared residuals for each of those, and we can sum all the areas of this square, and we can see that the red shaded area on the right is now greater than the one we had before. So the sum of the squared errors increased. So let's go back to our line of best fit, since it had a lower sum of squared residual that we also call sum of squared errors, or SSE. Let's look at what happens if we change the intercept now. Let's shift the intercept a little bit down. We can see that now some of the points are better explained by this line, but some are worse. Again, we can calculate the squared residuals and we can sum those up. And again, the sum of the squared residuals is larger with this new trend line than it was with the original line of best fit. So what we are doing when we perform a regression, we are minimizing the sum of the squared residuals, and that's what we define best.